Okay, so that's all the background. Let's talk about what happened to Tim Brown. So, he was an American. He had the good fortune to be living in Berlin when he developed leukemia. He was HIV positive and he also developed leukemia. And this is his doctor, Gero Hutter. And he went to his doctor and his doctor's like, okay, you've got leukemia. Well, probably didn't because I imagine he spoke German. But he was thinking about how to treat him. Okay, so the treatment is you're going to give him chemotherapy and then you're going to transplant him and you need to find a donor. So the good thing about Germany, unlike this room, is that 8% of the population are registered bone marrow donors in Germany. So that if you need a transplant in Germany, there's a pretty good chance that there's going to be many people in the donor database who will be a match to you. And Tim Brown was no exception. I think there were over 300 people in the database who were a good tissue type match. So what Dr. Hutter did that was unusual, especially as he's not an HIV doctor, he'd obviously been very well trained in Europe, you know, like they do. And he knew that CCR5 negative people were very resistant to HIV. So he had the idea, in those 300 donors that we have, that we can choose from to transplant Timothy, I wonder if anybody in there happens to be CCR5 negative. You know, just statistically, you'd imagine that maybe 3 out of them would be. So he ordered up some tests. He had to convince the hospital to pay for it. And he started testing all the donors to see if any of them was CCR5 delta 32 homozygotes, 2 copies of the mutant CCR5 gene. And I think the 65th sample they looked at, they hit gold, and they found a donor who was a good tissue match, but was also delta 32 homozygote. And luckily, that donor agreed to donate his bone marrow. So Tim went in, he got his chemotherapy to kill his leukemia, and he was transplanted with bone marrow from the donor. And he basically became a CCR5 negative individual himself. And the cool thing is that 4.5 years now since he had that first transplant, nobody can find any HIV in his body anywhere, despite the fact he's not been taking antiretroviral drugs. And just to show you what the data looks like in the paper, this is the levels of HIV RNA in Timothy's blood. So you see, starting off over here, he had hardly any, because initially he was on HAART. When he was first diagnosed with his leukemia, AML, they took him off HAART while they were giving him some chemotherapy drugs. And of course, his virus shot straight up because that's what HIV does when you take people off HAART. Then they put him back on the HAART. They got his virus loads back under control. That's over here. And then they transplanted him. He actually ended up getting 2 transplants, which is not uncommon. Sometimes the first one doesn't take very well. But now, as I said, 4.5 years since he had those transplants, there's no HIV in his body, and so that's why we talk about him as having been cured. Is that okay with everybody? Does anybody want to ask me any questions about that? They tested in different ways, yeah? Yeah, because when the German team first reported there was no virus in his body, those of us in this country went, yeah, send us your samples, we'll test it, okay? No, there's no virus. So he's been tested by multiple different labs, and there really is no virus in his body. Yeah?
Are you saying no virus or undetectable?
Ooh, a philosopher. I would have to say undetectable. Yeah, no. And I suppose I should say there is a possibility that there will be a tiny amount of virus there, and over time it may come back, yeah. No, that's, keep me honest. Okay.
Who was this transplant donor?
I don't know. It'd be kind of cool to find out, wouldn't it? They could have one of those things like before a baseball game where the recipient and the donor kind of get to hug and everything. That'd be kind of nice. Hallmark should do it. Yes?
Would you consider that a functional cure or?
Ooh, so it's tricky, isn't it? So I would have, before they did this, I would have said this is going to be a functional cure. The CCR5 negative cells are going to be able to keep the HIV at bay, but I bet there's going to be little bits of HIV if they look hard enough. But it actually looks like it's been a sterilizing cure. Now that may be because, as well as getting a transplantation, the chemotherapy he was given to sort of prepare, to get rid of his cancer really wipes out a lot of things. It wipes out not just his hematopoietic stem cells, but kind of wipes out most of his T cells as well. So it could be that because of the very extreme treatment he had, because he was somebody who was dying of leukemia, that actually also kind of got rid of a lot of the HIV-infected cells. Okay, but this is kind of an important point because the treatment he received, I mean, people sort of say to me, hey, sign me up. When can I get my bone marrow transplant from a CCR5 negative donor, okay? Whew, you do not want to have a bone marrow transplant unless you are, dying of leukemia. It has a very high rate of morbidity and mortality. You would not wish it on your worst enemy unless that's your best option for leukemia. So if we're not going to do bone marrow transplants from CCR5 negative donors to people who just have HIV infection, then the idea is that maybe we can kind of mimic this in some way. And the idea is that we would take a patient's own bone marrow hematopoietic stem cells out, and in the laboratory, we would engineer them so that at least a portion of them could be made CCR5 negative. And then we'll put them back into that individual and see what happens. And that's the sort of therapy that I'm working on with my colleagues in LA. All right, shall I tell you about it? Okay. All right, so the hypothesis of our work, because we are scientists, can we functionally cure HIV-infected individuals by providing them with HIV-resistant versions of their own cells? And it's certainly not a unique or new idea. Let's think about what cells we should be manipulating. Okay, so I've been telling you all about hematopoietic stem cells. They're over here. So they're stem cells, and all you really need to know about a stem cell is it's very long-lived, probably lives for your whole life. They're very rare. They're constantly dividing, replenishing themselves, and also kicking out sort of daughter cells, which then grow up and differentiate into all the different types of white blood cells and red blood cells you have whizzing around in your blood. And there's HIV over there, and HIV most famously infects CD4 positive T cells, but HIV down at the bottom also infects other cells, things like macrophages, microglial cells, cells that come from a different branch of the immune system. So if we're thinking about manipulating some cells to be CCR5 negative, certainly a really good choice would be to just straight away go after the CD4 T cells. I mean, that's 99% of what HIV is doing anyway, so let's target the cells that HIV targets. But if we target the hematopoietic stem cells, what I like about that strategy is anything you do to a stem cell eventually ends up happening in the daughter T cells and macrophages. So you kind of get to affect a much wider variety of cell types. And in addition, because hematopoietic stem cells are incredibly long-lived, you're potentially doing something that could be a one-shot treatment. You don't have to kind of think about doing it every year or every couple of years. Okay. Right, so engineering hematopoietic stem cells sounds scary, or at least if you knew a lot about it, it would sound scary. So first of all, it's not totally scary, because one of the things is that, let's look at the top point first of all. Outside of this room and this sort of field of HIV, people have been doing gene therapy, engineering hematopoietic stem cells now for about 15 years. And last time I looked, over 300 patients have had hematopoietic stem cell modifications in some way, not just for HIV, but for other, mostly genetic diseases, immune deficiencies, boy in the bubble disease, hemoglobin deficiencies, beta thalassemia. So there is quite a lot of expertise now in the world about how to engineer hematopoietic stem cells. And so all the trials that have been going on have shown us that this is feasible, we can do it, and it seems so far to be safe. But what's been disappointing, at least for the anti-HIV gene therapies that have been attempted, is that basically they haven't done anything. I think, what do I say? Efficacy has been low. That's kind of like a nice way of saying they've totally not worked. And we can think about why they've not worked. One of the main reasons is that it's been quite difficult to make modifications to enough cells to have an effect. In addition, when people have been engineering hematopoietic stem cells, they are typically adding to them a gene that will fight HIV. And those genes, although they look great in the lab, have just proven not to be potent enough to have an effect against HIV in a patient's body. And then, of course, the final problem we have is that if you add a gene to a cell that's going to fight HIV, you need that gene to sort of stay switched on in that cell for the lifetime of the patient and for all the daughter cells it produces. And that's quite challenging as well. You know, genes are very badly behaved. They just don't do that when you put them into cells. So these were all the sort of problems we have in the field, and it sort of made me and many other people think, how can we, if we want to make some CCR5 negative hematopoietic stem cells, yeah?
I don't know if you're going to answer this, but I was curious if there's a commonality between people that have that gene to where you could possibly do research to find out what that commonality is to maybe replicate it or have it work.
If they have the gene, you mean what's special about them, or how do they get it?
Well, how do they get it?
Okay. So, all right. We've got time. I'm going to teach you guys genetics. All right. Yeah? This is like me saying, I don't really know. No. So there's like strange things in human populations, you know. Sometimes you just find these weird genetic differences between us that shouldn't be there, but are. Oftentimes, a good example is something like sickle cell disease, okay? Sickle cell anemia. Horrible disease. Why the heck is it so prevalent, especially in African American communities? Well, it's very prevalent because people who have just one copy of the bad sickle cell gene are very, very resistant to malaria. So, okay, I'm in Texas. Do you guys believe in evolution in this state? Yeah? Okay, all right. All right, okay, just checking. Never know where I am. All right, I'm from LA. You can tease me later, right? Yeah, so there's been natural selection for what looks like a bad gene, sickle cell gene, because it protects people in Africa against malaria. So where the heck did CCR5 negative, if I tell you that 1% of, it's mostly Northern Europeans and Caucasians who have this gene, but for 1% of the population to have 2 copies of, basically be missing a gene, you have to sort of say, well, it must have had, done some good in the past. One of the things people always say, anything they find in Northern Europeans, they always say, it must have helped them be resistant to Black Death, bubonic plague, right? Because that's the only thing that happened in Europe in the past 1,000 years, okay? So some people think that maybe if you are CCR5 negative, you are more resistant to bubonic plague. Nobody's going to do the experiment, I don't think, of taking somebody and challenging them, but the other thing people believe is that it might actually give you a better outcome if you were infected with smallpox. So these are 2 very strong selection pressures that European populations have come up against in the last 1,000 years. But there's all sorts of quirky things in human beings, racial differences, just sometimes it might just be completely random. So, but I'm glad we have it. What it does tell us is that people who are CCR5 negative, they are almost, yes, completely normal. There are some subtle differences. I believe that if you get infected with West Nile virus, you're more likely to have a bad outcome if you're CCR5 negative. And I always say, HIV or West Nile? Yeah, I think I'll go with that. In addition, you're less likely to get rheumatoid arthritis. So there's some subtle differences, but I could be CCR5 negative, you guys could, we wouldn't know by looking at people, right?